This is Intro to Electricity Part 2. We'll be looking at electrical circuits in this presentation. And when we look at various materials, we can see that some of them, especially if we make measurements with them, we can see that some of them are insulators and some are conductors. We already said that the conductors are metals and insulators are non-metallic. It doesn't have to be a non-metallic element, it could be a non-metallic substance. So when you look at this image, where are your conductors and where are your insulators? Well, start with the conductors first. First of all, the pliers that we have here are metallic on the ends, and that makes them conductors automatically. If it's a metal, it's a conductor. We also have some bare wires that have been stripped here that also are copper, and they are conductors. Our insulators would include the insulation, actually what it's called, or the coating, the wrapping on the wire, and then we also have the plastic over the handles of the plier to insulate against electric shock as well. So when we look at an electric circuit, first of all, the definition of a circuit is a system of conductors and components forming a complete path for current to travel. Now, a few things about this. It does have to be a system of conductors. These conductors are often wires. And other components. Some of these components are used to control the circuit. Others are used to, for instance, do useful work as the circuit is working. And it forms a complete path. Okay, so the circuit itself is just a path, and this is the path specifically for electric current to travel. The properties, measurable properties of an electric circuit that we will be measuring and that we'll use to specify the details of a circuit include voltage, current, and resistance. Voltage is measured in volts, symbol is V. Current is measured in amperes, which is abbreviated amps, capital A for that, and resistance is in ohms, represented by an omega, capital omega. Okay, let's look at current first. Current is the flow of electric charge, which is measured in amperes. Okay, here we've got an analogy for a circuit. We've got a tank holding some water, so this is H2O, got a pipe leading away from it, and we've got a faucet out on the end with a valve. Okay, the analogy is that the tank is like the battery, the wiring, or the pipe is like the wiring, the passageway, and then this is like a switch that we can turn on and off. So when the faucet is off, is there any flow from battery to the outside? We would be looking for something coming out over here if we had something. And the answer to that is no. If the faucet is off, there is no flow. When the faucet is turned on, is there any flow? The answer there is obviously yes, it is. So following that analogy, if we look at the current in a circuit, when the switch is off, there is no current. When the switch is on, there is current. And the reason for that is that if the switch is off, off is a broken circuit. The mechanism of the switch itself opens the circuit, opens it so that there is a non-continuous conductor. The conductors end there. When the switch is on, we have a continuous circuit or continuity, and we have a continuous set of conductors from one side of the battery to the other. We can also see that current is on because something is causing the light bulb to turn on, to glow. Okay, when we look at current flow, we have two different types of current that we could be considering, and we have to be specific as to what it is that we're actually looking at. One of those is conventional current, which assumes that current flows out of the positive side of the battery through the circuit and back to the negative side. So we have something flowing. This is the symbol for a battery over here. So from the positive side, we have arrows showing that the current is flowing in this direction to end back at the negative side. This was the convention established when electricity was first discovered, but it's not really correct scientifically speaking. Electron flow is what actually happens, so in reality we have electrons that are repelled from the negative side of the battery, and they are going to move around in the opposite direction of what our conventional flow would, because they're attracted to the positive side. And what the conductor does is it provides a pathway to get from the negative side to the positive side. In the battery, the electrons can't flow directly from the negative area to the positive area in the battery. If it did, we would have a, quote, short circuit, and nothing would flow out here. So, engineering versus science. The direction of the current flow doesn't really matter in terms of how you consider it. We can consider either way, and we're going to get exactly the same results from calculations as well as hooking up circuits, regardless of the way that we choose. So both conventional current and electric flow are used in various places. In general, in science disciplines, physics, for instance, physical science, we think electron flow. Whereas in engineering, we tend to use conventional current and think about the flow of positive charge. Since this is an engineering course, we're going to use conventional current. But there will be times when we still switch over and talk about electrons flowing. In fact, this particular presentation started in part 1 talking about electron flow, but now with conventional current we're talking about positive flow. Okay, voltage is the next quantity that we would want to look at. Voltage is the prime mover. It's what makes current flow. It's the push. So it's the agent that causes current to flow. It actually represents potential energy, and it isn't measured in volts. Sometimes you'll see this as a force or an electromotive force, but it is not really a force in the formal definition of force. So we'll call it a prime mover. It's something that gives the conditions under which current can flow. As an example, besides this, let's suppose we had a river, and we have the river at the top of a hill. Okay, so we've got a river at the top of a hill, and we know that water is going to flow downhill. We can say that because of the setup of the water being at the top of the hill to begin with to the bottom of the hill, there's a potential energy difference that will cause the water to move in the direction of lower potential energy toward the bottom of the hill. So we could say that gravity in that case is a force, but gravitational potential energy is what's actually the prime mover in that case. So same thing with voltage. Voltage is a potential energy condition, and current is going to flow from an area of high potential energy to low potential energy, or high voltage to low voltage. We measure voltage in volts, and looking at our analogy again, when the faucet is off, the switch is off, is there any pressure? And be careful about that as you're thinking about it. The answer is yes. The pressure is, the voltage is pushing the pipe. If you were to pop a hole in this pipe right here, you would have water spurting out of it from the pressure. So yes, there is pressure. When the faucet is on, is there any pressure or voltage? And the answer is again yes. Pressure or voltage pushes flow or current through the system. On the other hand, if the water dropped to, let's say, this level, then we would say that there is no more flow. The potential energy is not great enough to, if it's above this, level, the level of the pipe, then we could say that water will flow. But if it's down here, it's not going to flow. So looking at voltage in the circuit, battery provides the voltage that will push current through the bulb when the switch is on. And if the switch is on, we're going to have current. If it's off, we have no current. And again, that's because of the we have pressure in both cases. There's a voltage here across this battery. This is 1.5 volts, like any D battery. And as we look at this scenario where this is turned on, this is still 1.5 volts. So the voltage isn't changing except as the chemicals are used up inside the battery. All right, resistance is the third term that we have to be concerned with, is the opposition of current flow. This is measured in ohms, named after someone. This is the capital Greek omega. And this would be like, for instance, it says if a rock gets lodged in the pipe, what happens to the flow, or what happens to the current? And the answer is that it's going to slow the current down. So if we have a clog in the pipe, things aren't going to run through as quickly. So flow is going to decrease, or the current decreases. So if we have a switch and a battery and a light bulb, resistors are components that create resistance to current. And one of those, for instance, here, a light bulb is a resistor. And very often, as the voltage decreases, as it goes from one side of this bulb to the other, we're going to have a generation of heat. So very often resistors heat things up because there's a push on one side of them, and as electrons push through them, they lower in energy. Reducing current causes the bulb to become more dim. So if we had something here, if we put a resistor in the circuit, we go back a slide, have our resistor here, that's this one, but if we put the resistor into the circuit, the bulb is going to glow more dimly. So the bulb itself technically is a resistor, but if we add another piece of equipment known as a resistor into the circuit, so that we really have two resistors, this resistor lowers the current, and lower current leads to lower lighting of the bulb. Let's talk about measuring these things. So measuring voltage first. Okay. We have a piece of equipment that we have over here. Let's see if I can get a pen. It is a multimeter, and a multimeter is going to measure, obviously, multiple things. And one of those things could be voltage. So we will set the multimeter to the proper voltage range. This appears to be a 9-volt battery, so we would want to be in the range that would allow us to measure that. So we're set on the volt DC section over here, we're set to 20 versus 200 or 2000 milli is what that stands for, millivolts. So we're in the 20 range. That's relatively close to 9 volts, closest we've got on from our choices at least. And we measure across a component. So for instance, maybe we're interested in the switch, or maybe we're interested in the battery, or maybe we're interested in this diode over here, a light. If we want to measure the voltage, we measure across it, meaning that we put one of the probes on one side, one on the other side. When we go to the switch, we measure from this side. Notice that we've got, this is our positive probe, this is our negative. We're putting the positive on the positive side, the negative on the opposite side. And what's happening is that we've got out here, we've got our multimeter connected. So as we do that, we're actually opening up a separate pathway to look at the voltage from one side to the other. And you can see we're doing that on all of those. An instrument that's used to measure the properties of an electrical circuit, including voltage, current, resistance, is the multimeter, as I've already said. And there are multiple versions of it. We have a couple of different versions here. To measure current, we set the multimeter to the proper DC range. We're dealing with DC electricity at the moment, and probably throughout this course, direct current instead of alternating current, which is AC. So we're going to be in the DC range over here, and we're setting this to 20 M, which is 20 milliamps would be our range. And the circuit flow has to go through the meter. So what we do is we open up the circuit, we remove the wire, and we replace the wire with the multimeter. So we've got the positive side here, the negative side there, and our circuit is completed by the multimeter itself. So any current, if we're looking at current flowing from positive, is going to flow into the meter and then out of the meter, so to speak, which is not really the way current works, but just go with me for right now, and then continue on in the circuit. Okay. Measuring resistance, we set the multimeter to the proper ohm range, and sometimes you don't necessarily know exactly what that is to begin with, so you have to experiment a little bit. This is saying we're around 20K, which would be 20,000 ohms. We measure across the component being tested, and we remove the power source. So power has to be turned off or removed from the circuit altogether. So battery comes out. The battery of the multimeter is going to take the place of it. It's going to try to push current through a component that we're interested in, and we measure the resistance that way. Across the resistor, across the light, and so forth. Now, mathematically, voltage, current, which is I, and resistance, R, are related to one another in a mathematical equation. This equation is known as Ohm's law, and what it says is the current in a resistor varies in direct proportion to the voltage applied to it and is inversely proportional to the resistor's value. Okay, so the current, I, varies in direct proportional to the voltage, V, and inversely proportional to the resistor's value. So I equals VR. And of course we have our abbreviations. Voltage is V, I, and R. If you know two of the three quantities, you can solve for the third, and we'll of course will be just using simple algebra. So this equation that I've written up here, which is the equation statement of this verbal statement, can be written in multiple ways. If I cross multiply, this is over 1, I'm going to have I times R equals V. That's what I've got here. I equals V divided by R, which is what I've got here. And then if I solve for R, R is going to be equal to voltage divided by current, V over I. So as a simple example of Ohm's law, the flashlight that's shown here uses a 6-volt battery and has a bulb with a resistance of 150 ohms. When the flashlight is on, how much current will be drawn from the battery? All right, so here's your schematic of the diagram. Now, notice the diagram versus the description up here. We've got a resistor, which is a light bulb. The symbol for the resistance is here. So this symbol is resistance or resistor. And in this case, it's a bulb. We've got this symbol, which is the symbol for a battery. This is the positive side. This is the negative side. And anytime we have that symbol, that represents a battery. It's shown in 6 volts. The resistor is 150 ohms. And we've got current that's flowing in this direction. I is going to be here, and it's going to pass through the resistance. Okay. When the flashlight's on, how much current will be drawn from the battery? Okay, so I equals V divided by R. Excuse me, I just said one thing and wrote another. I equals V divided by R. So we're interested in the current. So I equals V over R. 6 volts is the voltage. 150 ohms is the resistance. And 6 divided by 150 is 0.04 amps. And they're representing this in milliamps. To get from amps, 0.04 amps. There are 1,000 milliamps in 1 amp. So we have typical metric conversions using dimensional analysis that you've been exposed to before. And 0.04 times 1,000 would be 40. Amps cancel. And we end up with milliamps. Most important part, however, is this: the equation, the substitution, the final answer.